have derived the transmissibility equations, which represents the ratio of the force transmitted to the receiver to the force excited by the source. And now we want to see how the transmissibility is changing with the excitation frequency. So let's say we put the natural frequency here, because there will be the case where the excitation frequency matches the natural frequency. We will make analysis for 3 frequency regions: the low frequency well below the natural frequency, the frequency close or the same as the natural frequency, and the high frequency well above the natural frequency. The first case is where the excitation frequency is much lower than the natural frequency, where omega over omega n is much smaller than 1. So in the numerator, the second term is much smaller than 1, and the whole thing here equals to 1. In the denominator, omega square over omega n square will be also much smaller than 1. So this term in the bracket is 1, and the second term here will also be much smaller than 1. So the transmissibility at low frequency is 1. Let's put the value of 1 here. So what it says is that at low frequency away from the natural frequency, the transmissibility is approximately 1. Now let's see the second case where the excitation frequency is the same as the natural frequency, or omega over omega n equals to 1. Here the omega over omega n is 1, so we have 1 plus 4 zeta square. And for the denominator, this 1 minus 1 equals to 0. And this is 1, so we have only 4 zeta square. Now zeta is usually small values for most engineering structures, typically 0.01 up to 0.1. So 4 zeta square is much smaller than 1. So we have 1 over 4 zeta square root, so this is equal to 1 over 2 zeta. This actually tells us that when the excitation frequency matches the natural frequency, the transmissibility is 1 over 2 zeta. Let's denote 1 over 2 zeta here. So approaching omega n, the transmissibility will increase and peak at 1 over 2 zeta. The last case is when the excitation frequency is well above the natural frequency, or omega over omega n is much larger than 1. So let's say omega square over omega n square is 1 million. So this term here will be much larger than 1. Then we can ignore 1, and this will be only 4 zeta square omega square over omega n square. Again, for the denominator, assuming this omega square over omega n square is 1 million, so we can ignore 1, and because we have power of 2 outside the bracket, so we have omega over omega n to the power of 4, and this will be much larger compared to omega square over omega n square. So we can ignore the second term, and we have omega to the power of 4 over omega n to the power of 4. We can cancel out this one, square root the whole thing, so we get 2 zeta omega n over omega. This indicates that as the excitation frequency increases, the transmissibility is reduced. So this curve is controlled by 2 zeta omega n over omega. Okay, let's analyze again the graph we have here. At low frequency, well below the natural frequency, the transmissibility is 1. What does it mean? As its transmissibility is the ratio of the transmit force and the excitation force, T equals to 1 means the transmit force is equal to the excitation force. So if the machine excites with 1000 Newton, the transmitted force to the receiver will also be 1000 Newton. Here, no reductions of the transmitted force as we expect. Now, as the frequency is getting closer to the natural frequency, the situation becomes even worse. The transmissibility is greater than 1. So the transmitted force will be greater than the excitation force. Let's say zeta equals to 0.1. At omega over omega n, then 1 over 2 zeta will be 5, which means the transmitted force to the receiver will be 5 times the excitation force in case of resonance, the dangerous case where we should avoid in engineering. At high frequency well above the natural frequency, this is where the transmissibility rolls off with the frequency. And we can see here that this is the frequency region when transmissibility is less than 1, which means the transmitted force is less than the excitation force. And this area, we call it area of isolation. Below this frequency area, when T is equal or greater than 1, we call it area of amplifications. We can see here there is an intersection frequency where after this frequency the transmissibility starts to be less than 1. So what is this starting frequency? At this frequency T equals to 1, and assuming the damping loss factor is very small or close to 0, we can simplify the equations to T equals to square root of 1 over 1 minus omega square over omega n square square. Before we eliminate the power of 2 and the square root, we should take note that T cannot be negative, so it must be always positive. There is no negative value of transmissibility. We can see here that the intersection frequency is above the natural frequency, which means omega over omega n will be more than 1. If we insert it here, the terms in the bracket will be negative, but because we have the power of 2 outside the bracket, then all the values in the bracket will become positive. So if we cancel out the square with the square root, we have to make sure that these positions must be interchanged. So we will write down this as T equals to 1 over omega square over omega n square minus 1. Okay? So if the transmissibility equals to 1, we can rearrange this to have omega square equals to 2 omega n square. And we end up with omega equals to the square root of 2 multiplied by omega n. So the intersection frequency here is square root of 2 multiplied by omega n. This means to be in the area of isolation, the frequency of excitations must be larger than this square root 2 omega n. Usually we cannot control the excitation frequency, so in other words, we have to control omega n so that it is smaller than the excitation frequency over square root of 2. And how to make omega n small? Remember that omega n is equal to square root of k over m. So to make omega n small in this case, should we increase the mass or should we reduce the stiffness? The latter one is what engineers do in practice, which is to have a flexible mounting between the source and the receiver. We can see some examples in applications like the rubber mount and also the helical springs. These flexible mounts are usually called vibration isolator. So for the case of this centrifugal machine, we should put the vibration isolator in between the feet of the machine and the floor. Alright, in the next video we are going to discuss the frequency analysis of the transmissibility in a bit more details. For example, how small is the value of the stiffness constant, and what are the effects of damping to the transmissibility. I'll see you in the next video. If you like this learning content, please subscribe to my channel Azma Putra, or you can visit my website www.azmaputra.com.